In this video, I want to talk about the displacement. Before, we looked at the position, which we found was a vector function of time, a function where you input a time, and we got a vector that told us the location of an object at any time. And this location then was referenced to a coordinate system, so this assumes some sort of coordinate system through which this was defined. Okay, so the position function tells us, or can tell us, the position of an object at any time. Now, I want to do something specific. I want to choose two times. Two specific times, and I'll call them my initial time, which my notation is t sub I, and my final time, which I'll identify with notation t sub f. So given these two times, we can calculate the object at those two times by the position function, which is the function evaluated at the initial time, and the function evaluated at the final time. Now, at this point, we're going to do even a little more notation. This may be a lot to write, and in fact, a lot of books and everything else will introduce a new sort of shorthand notation for this, which is just some initial vector r sub I and some final vector r sub f. And so this is certainly easier to write, but you can't ever forget what this means. This is simply the position function evaluated at the final time, and this one is the position function evaluated at the initial time. In fact, sometimes you might have books that will call this r sub 1 or r sub 2 or x sub 1, x sub 2 if you're in one dimension. So there's all sorts of different notation, but it's important to understand what that means. So let me take a minute. This will be a recurring theme, is that it's never that useful to memorize notation. R, t sub f, r sub f, r sub I, x sub I. It's most useful to memorize the words of what this means. This is the position function evaluated at the final time. This is the position function evaluated at the initial time. Words are easier to remember, and then you can use any mathematical notation you want to represent it in your own work, as long as you always understand what that means. Okay, so now that I have I've identified the position of my object at two specific points in time, I can define the displacement. The displacement. And we'll give the displacement, we'll call delta r. So this is not delta times r or anything. This is one object. This is a vector that I'm defining given this notation. The delta is often means difference. And so this is one object, one vector, and it's defined as this final vector minus the initial vector. So this is a displacement. Again, you can see kind of how useless it would be just simply to memorize this equation, because this already assumes you've chosen two specific points in time of a trajectory, and it describes the vector difference between those 2 points in time. So you really have to understand what this means in words to be able to use it effectively. So, but let's just look at examples. We're going to look at our different types of motion and calculate displacements. All right. So our first we have our this is our toy car. We're going to say that's zooming across a table, and so from before, we found that the car was at 0 at t is equal to 0. It was at 2 at t is equal to 1, So t to 0, 2, it was about at 8, at t is equal to 1, it was at x is equal to 2, t is equal to 2, it was about x equals 8, and t is equal to 3, it was about at x equals 18. All right, and so we were able to identify then the position vectors at these 4 points in time. This is our motion diagram. At r is equal to 0, it was 0. At 1 second, then our vector was 2 centimeters long, pointing in the positive x direction. At 2 seconds, our vector was 8 centimeters long, pointing in the positive x direction. And at 3 seconds, it was 18 centimeters, pointing in the positive x direction. So let's calculate some displacements. First, so let's let, we got to choose 2 points in time. And so first, let our t initial equal 0 and t final equal 1. So that's these two vectors. Then our displacement, see if I'll use a darker blue here. Our displacement then is the vector evaluated at t final minus the vector function evaluated at t initial. Well, this is just 0, and so we are simply left with the vector function at time is equal to 1. So our delta r then, we'll call this this is delta RA, we're going to do a couple of these, try to distinguish them then, is simply 2 centimeters in the positive x direction. Okay, well, okay, fairly easy enough. Let's look at 2 other points in time. This one we'll use as our t initial to be time is 1, and our final time to be 2. So in this case, our delta r, we'll save the blue for the vectors. A delta r then is equal to the vector function evaluated at 2 minus the vector function evaluated at 1. And so now we need to take a look at both of these vectors. Okay, so if we first of all take this vector here, that's this one, so we'll translate that down here, which we can do here. And now I need to subtract the first vector from it. So if we subtract graphically, the first thing that we do is we switch this vector, take the vector evaluated at 1, and point it in the opposite direction. So that would look like this. Then we add it to the first vector. By adding graphically means we take the tail and put it to the tip of the first one. And put it on top of it. I've displaced it slightly so we can see. And then the resulting vector starts from the tail of the first and goes to the tip of the second. So this vector is now the second displacement, the displacement between the vectors evaluated at t is equal to 2 and t is equal to 1. All right, let's do the next one. So now I'm looking at my initial time to be 2 and my final time to be 3. My displacement then is my vector function evaluated at 3 minus my vector function evaluated at 2. So now I'm going to add these graphically. And this one was this long one evaluated. Well, did I go be a little far on that one? 18 centimeters long, pointing in the positive x direction. Now I need to subtract from it the vector evaluated at t is equal to 2. So the first thing to do is take this vector, point it in the opposite direction, then put the tail of it to the head of the first. And so that's the minus the r evaluated at 2. Then the resulting vector starts from the tail of the first and goes to the head of the second. And so this is now the displacement vector, call r sub c, between the vector evaluated at those two times. Okay, so the other thing we can do is since this is all in one dimension, we can come up with what these vectors are. Here at b, here, the first vector went 8 centimeters in the positive x, and then went 2 centimeters in the negative x, so we know that this resulting vector is 6 centimeters, and from looking at it graphically, it points in the positive x direction. And so for this one, C here, this first vector went 18 centimeters, 18 centimeters in the positive x direction, and then we went 8 centimeters in the negative x direction, so our resulting vector, displacement vector, is 10 centimeters in the positive x direction. And that was all done graphically. I've sort of gone through it in all the detail here. But what I want to point out now is let's go back to the motion diagram and see where these vectors show up on the motion diagram. So the first displacement vector is 2 centimeters long, and that fits exactly between the first and second point on the motion diagram. The second vector here, which is 6 centimeters in length in the positive x direction, fits exactly between points 1 and 2 on the motion diagram. And then this vector, which is 10 centimeters in length and points in the positive x direction, points from the second point to third point in the motion diagram. So you can see, this is important, how the displacement vector fits on the motion diagram is that each point on the motion diagram can be defined by a vector of the position function referenced to some coordinate system. But the displacement vector, which is the vector difference between successive position vectors, is the vector that points from the initial object's location to the final object's location for each 2 points in the position function that you calculate.